Hi science friends. Today we're going to talk about solutions. So solutions are, you don't usually find water naturally in the environment. Water, like we've talked about, is a very polar molecule, and so things naturally dissolve in water. You don't just find, lake water is not pure water. Even like water vapor is not pure water. You just don't find pure water. And so what we see instead are aqueous solutions. And so they're samples containing dissolved substances. And when we have an aqueous solution, we have a solute, which is the particle that's dissolved in, and the solvent, which is the dissolving medium, such as the water, what's dissolved in it. So for example, when we have salt water, salt is the solute and water is the solvent, okay? So ionic compounds and polar covalent compounds, they dissolve nicely in water because they have those opposite attraction and charges. Remember, water has got the positively charged the positively charged hydrogen, the negatively charged oxygen, and so those polar covalent molecules are going to be attracted to the opposite charges. Same thing with the ionic compounds because they have a positively charged cation or a metal and a negatively charged anion or a nonmetal, and so those are going to be attracted to those opposite charges as well, and so they dissolve easily in water. Now, non-polar covalent molecules do not dissolve well in water, and that's really important. They don't have that difference in electronegativity or difference in charge that allows them or causes them to kind of attract toward one another. Okay, now this process of dissolving is referred to as solvation. And so what we see here, we've got our water molecule with the partial positives on the hydrogen, the partial negative on the oxygen. And so this is a crystal of sodium chloride. Sodium chloride or salt is an ionic compound. You've got that metal sodium with the positive charge, the non-metal chlorine with the negative charge. And so what you see here is when we have these water molecules, that partial negative charge orients itself, the oxygens orient themselves towards the nitrogen because of those opposite charges. Versus down here, the hydrogen, which has the positive charge, orients itself to the negative chlorine. And so these are referred to as solvated. When something dissolves, we say that it is solvated, meaning it's surrounded by those solvent molecules. The solvent, or the water here, surrounds the chlorine, and so that is solvated. That's what happens when something dissolves, okay? Now, let's jump just a little bit to electrolytes. Sometimes in solution, you will have solutions that are electrolytes, meaning they conduct electricity, okay? Maybe after you're, playing sports or exercising or something like that, you drink Gatorade because Gatorade has electrolytes, and that's good for your body. When you sweat, you lose a lot of electrolytes, and electrolytes are really good for your body because your body, nerve impulses travel through electrical impulses, and so we have to have that difference in charge. You have to have those electrical impulses to make those nerves fire. And so if our electrolytes get too low, then we need to be able to replenish them. So all ionic compounds are going to be electrolytes, okay? Now, on the other hand, non-electrolytes do not conduct electricity. So most carbon compounds and then many covalent compounds are going to be non-electrolyte compounds, solutions, okay? So these are two different types of solutions, electrolyte solutions and non-electrolyte solutions. So once we have our electrolytes, they can be considered a strong electrolyte or a weak electrolyte. So strong electrolytes are going to have mostly individual ions in solution, and then weak electrolytes are only going to have a small amount of ions in solution. And so what that means here we see no ions. We have the molecules that are still formed. They don't separate or break apart into the positive charge and the negative charge, okay? And so that's why ionic compounds are frequently strong electrolytes because they easily break apart into that positive and negative charge, okay? Here is a weak electrolyte. So you see some positive and negative charges that have separated from one another, but many of them are still bound together, okay? And so that's a weak electrolyte. When you put a strong electrolyte in a non-electrolyte into a conductivity meter, the light bulb doesn't light up. There's no electricity that's going to flow there because electricity travels because of these charged particles. If you have a weak electrolyte, you'll light the bulb, but it'll be relatively dim, okay? Versus a strong electrolyte, what you see, maybe, is that these particles have completely broken apart. There's lots of ions there. There's not a lot of combined particles. So these particles have completely separated. Sometimes we refer to it as dissociation. They separate from one another. They break apart. And as a result, these are going to conduct a lot of electricity. And you see that light bulb glow really bright, okay? So strong electrolyte solution, weak electrolyte solution, non-electrolyte solution, okay? So those are solutions, all right? Now, we're going to talk about two other types of things. Solutions, backing up just a second, are homogeneous mixtures. We talked about those way back in like Unit 2 when we talked about matter. Homogeneous mixtures means they're the same throughout, okay? If you, were to drink it, it's going to all be the same. You're not going to have chunks or anything like that. It's all the same throughout. It's uniform, all right? Now, the next type of mixture that we're going to talk about is a suspension. And in suspensions are heterogeneous mixtures, meaning they're different throughout. And so in suspension, we have particles that settle out upon standing. You see that in this Italian dressing. This really separates there. They settle out. We could filter this and separate it, okay? If you filter a solution, it doesn't separate out. Back at the very beginning of the year when we did that separation of a mixture lab, you had salt, sand, and iron, okay? The sand made, the salt and the water was a solution, okay? The sand would be kind of like a suspension because it separated out. We filtered the sand out. But when we ran that salt water through the coffee filter, the salt water came on through with the water because the particle size is very small. In a solution, you have a very small particle size. In a suspension, you have a large particle size, and so it separates out. Okay? Now, the last type that we're going to talk about is a colloid. And so a colloid kind of goes between a solution and a suspension. So it has a medium particle size. It's kind of in between homogeneous and heterogeneous. It's in between. Okay? It's not fully homogeneous, but it's not fully heterogeneous. And so colloids, they are mixtures with two separate states of matter. So let's look at this diagram and see if we can make sense about this. Colloids, the particles can't be filtered out like solutions, and they don't settle out like solutions, okay? But they're not quite as good as solutions, all right? So for example, fog. In fog, you have a gas medium, but it has liquid particles in it. You have liquid rain in that gas, and that makes fog, okay? In smoke, you have solid particles, dust and debris, in a gas medium, so that makes smoke, okay? Whipped cream, you have cream or fat particles. You have air bubbles in a liquid medium, okay? That makes whipped cream. Milk, that's the one I was thinking of. You have the liquid fat particles. You have the cream in that liquid medium, okay? That makes milk. And so on and so forth. Blood, you have those solid blood cells in a liquid plasma medium to make up blood. All right, and so on and so forth. So you see you have a medium phase and then another phase that's kind of dispersed throughout the medium. Naturally, when you think of something like whipped cream, you kind of think of it as a homogeneous mixture. Your whipped cream is basically the same throughout, but it's a colloid because there's gas bubbles in that liquid medium, okay? Now, another difference about colloids is they exhibit the Tyndall effect. And so what that means is they scatter light when you shine it through them. Suspensions also do this. Solutions don't do that, okay? So it's the scattering of light by a suspension or a colloid is what the Tyndall effect is. All right? And then the last thing we're going to talk about today is an emulsion. So an emulsion is a type of colloid of two or more liquids that generally don't mix. So they're liquids that are generally insoluble in one another, okay? So for example, oil and vinegar. Oil and vinegar are used to make mayonnaise. When you think about mayonnaise, it's pretty much even throughout, right? It's an example of an emulsion. Oil and vinegar, though, if you took oil and you took vinegar and you poured them in a measuring cup together, they would completely separate out, okay? But if you add an egg, it's called an emulsifying agent. The egg is an emulsifying agent. It actually causes them to come together, okay? So here's our oil. If we put oil and vinegar in a cup together, and here's our vinegar. Oil is less dense, so generally it'll float right on top of the vinegar, okay? Now you can kind of mix it and shake it up and they'll mix for just a second, but then it'll start to come back to the top and settle out. But if you add that egg, if you add that emulsifying agent, what's unique about it is it has one end that's polar and one end that's non-polar, okay? This polar end likes the water, okay? The polar end likes the vinegar, so to speak. The non-polar end hates the vinegar. It likes the oil, okay? We use these terms hydrophilic, meaning water loving, and hydrophobic, meaning water hating. And so the oil is going to go in the middle by these hydrophobic tails. And then the water or the vinegar, a vinegar is a solution of acetic acid in water, is going to be on the outside by the polar heads, the water-loving heads. And so you can't hardly see it in this diagram, but these oil molecules, which are represented by the orange, are surrounded by these little circles. And the circle essentially represents this emulsifying agent. And so when you surround them with that emulsifying agent, we get what we see in picture D. It's an emulsion. It allows two things like oil and vinegar that generally don't mix to mix up nicely and form something like mayonnaise, okay? So it's a type of colloid that has an emulsifying agent in with it, all right? So you have an assignment today. In Google Classroom, there is about a 20 slide flashcards, and you have a paper. Actually, I may have forgotten to give it to you. No, I think I gave it to you. If I forgot to give it to you, you can just write it on notebook paper. But you have a paper where you're supposed to, for each of the flashcards, say if it's a solution, a suspension, or a colloid, okay? So work on that. I don't think any of them you have to identify specifically as an emulsion, But if you think that you see one that is an emulsion and you want to put it on there, just write it out to the side. I'll give you extra credit for it if you're right. Okay? Let me know if you have any questions, and if not, then you'll have a great day.